What if everything you thought you knew about the universe was wrong? From the moment we wake up until the moment we sleep, we trust that the world around us is real, that the ground beneath our feet is solid, the sky above us is expansive, and time flows steadily forward. But modern physics is challenging these fundamental assumptions in unprecedented ways. Experiments in quantum mechanics suggest that reality may not be as stable as we've always believed, or perhaps, not even real in the sense we understand. Some have begun to wonder if the universe is an illusion, a grand cosmic sleight of hand. Let's dive into these bizarre discoveries and see how they force us to question whether the universe truly exists the way we think it does. Hello everyone. Tonight, we journey from the warping of space-time to the whispers of probability, searching for glitches in the programming of our world. It's a long story, so let's begin the dream. Before we start, don't forget to like and share. The EPR paradox, named after Einstein, Podolsky, and Rosen, was a thought experiment proposed in particle is measured, the other responds instantaneously, and there is no apparent way to explain this through hidden variables or local effects. This led to a profound divide in the scientific community. On one side were those like Einstein who believed the theory was incomplete, and on the other were those who accepted that the universe might be far stranger than imagined, with non-local connections playing a fundamental role in the fabric of reality. For decades, the EPR paradox remained unresolved, but it sparked intense debate, forcing physicists to question the foundations of their discipline and face the possibility that reality is not as intuitive as it seems. This shift was crucial for modern physics, paving the way for new theories and experiments that further challenged the classical worldview. One of the most significant advancements came in the 1960s from the work of physicist John Bell. Building on the EPR paradox, he proposed what is now known as Bell's theorem, bringing these abstract questions into the realm of experimental testing. Bell's theorem wasn't just a hypothesis, it provided a mathematical framework to determine whether the universe was truly local, as Einstein hoped, or if it followed the weird, non-local rules of quantum mechanics. A subsequent series of experiments showed that local hidden variables could not explain the behavior of entangled particles. The results confirmed that the universe does not function in a strictly local way. For Einstein, who passed away in 1955, this would have been a disappointing conclusion. He had hoped deeper physical insights would restore a predictable, local universe. But Bell's theorem and the experiments that followed suggested otherwise. The universe is fundamentally interconnected in ways that classical physics cannot explain. Thus, the EPR paradox evolved from a challenge to quantum mechanics into one of the strongest pieces of evidence supporting it. Our experience of the universe is built on our senses. We trust that what we see, hear, and touch is real. The tree trunk feels solid, the sky looks blue, and gravity pulls us toward the ground, all creating a stable, predictable world. But what if reality isn't as solid as it seems? What if the world we experience is a mirage shaped by the mind? For centuries, philosophers have asked about the nature of reality. Does the world exist independently of our perception, or is it entirely shaped by our experience? Plato imagined the world we see is merely a shadow of a deeper, truer reality. Others suggested that everything we know might be a construct of the mind, a projection that feels stable only because we need it to be. Modern science has added a new layer to this ancient debate, particularly through quantum mechanics, which has shaken many of our classical notions of the cosmos. At the microscopic level, the behavior of matter is far from intuitive. Particles can be in multiple places at once, distant objects can influence each other instantaneously, and some things seem to exist only when we observe them. This counterintuitive behavior forces us to seriously examine the meaning of reality itself. Every day, experience tells us the universe follows clear rules. A dropped cup breaks, and walking across a room moves you from point A to point B. But quantum mechanics shows these rules may not hold at a fundamental level. The particles that make up everything behave in ways that defy common sense. For example, a particle does not have a definite position until it is observed. This is known as superposition. Before measurement, a particle exists in a probability cloud, occupying many possible states simultaneously, and only chooses one when we look. If the universe only takes on a definite form when we observe it, can it still be called independent of us? Is reality fixed and solid out there, or is it something fluid that emerges through our interaction? This brings us to the role of the observer. Quantum mechanics implies that we, as observers, play a key role in shaping the universe. The famous Schrödinger's cat thought experiment illustrates this perfectly. A cat is placed in a box with a device that has a 50% chance of killing it. Until the box is opened, the cat is considered both alive and dead. Only when an observer opens the box does the cat's fate become a reality. This experiment highlights the absurdity of quantum mechanics and suggests that reality may depend on our observation. This line of thought echoes certain Eastern philosophical traditions, such as the concept of Maya in Buddhism, which posits that the reality we perceive is not the ultimate truth but a veil obscuring a deeper reality. Similarly, modern physics may be revealing that our experienced universe is just a veil, beneath which lies a much more complex and non-intuitive truth. One of the most striking challenges posed by quantum mechanics is entanglement. When two particles are entangled, they remain linked regardless of distance. Changing the state of one instantly changes the other, even if it's on the other side of the galaxy. This seems to violate our understanding of space and time, suggesting that distance and separation might be fundamental illusions. Bell's theorem turned the confusing implications of the EPR paradox into something testable. Before Bell, debates over quantum mechanics were largely theoretical. EPR raised serious questions about whether the universe was governed by local interactions but lacked a clear path for experimental verification. Bell changed that. He showed how to determine if the quantum world truly violated classical intuition. The breakthrough of Bell's theorem was that it didn't just ask if hidden variables existed, it provided a set of mathematical inequalities that could test whether hidden variables could maintain the principle of locality. If quantum mechanics was correct, experiments would violate Bell's inequalities. If Einstein was right, the inequalities would hold, meaning hidden variables were at work. In the 1970s and 80s, scientists began conducting these experiments. The first major test occurred in 1972, led by John Clauser and Stuart Friedman, marking the first real attempt to see if entangled particles defied local hidden variables. Another pivotal experiment was completed in 1982 by Alain Aspect's team in France. The results were clear: Bell's inequalities were violated. This meant no local hidden variables could explain the behavior of entangled particles. Far apart particles could influence each other instantaneously, as if the constraints of space-time itself did not apply at the quantum level. Bell's theorem showed that entanglement is not a theoretical quirk but a fundamental aspect of how the universe works. The behavior of entangled particles cannot be explained by any classical means, indicating that quantum mechanics points toward a reality that contradicts daily experience. One exciting consequence of Bell's theorem is that it opened the door to new technologies. Entanglement moved from a strange curiosity to the core of cutting-edge applications, such as quantum computing and quantum cryptography. In quantum computing, entanglement allows information to be processed in ways that far exceed classical computers, solving complex problems at speeds unreachable by traditional means. In quantum cryptography, the unique properties of entanglement provide entirely new ways to secure communications, as any attempt at eavesdropping would disturb the entangled state and be immediately detected. Because entangled particles can share information instantaneously, it suggests that information itself may not be limited by physical carriers in the way we expect. Some physicists even speculate that information is the most fundamental building block of the universe, more basic than matter or energy. Quantum entanglement remains one of the most baffling and fascinating topics in modern physics. To grasp its significance, we need to step back and consider its implications for our view of reality. In classical physics, events are separated by space and time, and causality follows a clear order. If you throw a stone into a pond, the ripples spread outward from the point of impact. You can trace the effect back to the cause, and the connection is bound by the laws of space-time. But entanglement shakes this clear connection. Imagine two entangled particles, one on Earth and one on the other side of the galaxy. If you perform a measurement on the one on Earth, the distant particle's state immediately matches the result, even though no information had time to travel between them. This instantaneous connection seems to bypass the rules of the classical world, suggesting they act as part of a single, deeper system that is unaffected by distance. Entanglement, first and foremost, challenges our understanding of causality. In the classical world, the cause always precedes the effect, and the sequence is unmistakable. In the quantum world, however, entangled particles don't seem to follow this linear order. The measurement of one particle instantly influences the state of the other, with no discernible chain of causality between them. This suggests that at a more fundamental level, the universe may not operate under the strict causal rules we observe in our daily lives. Some physicists propose that within this reality, space-time itself isn't what we thought it was. It's not that entangled particles are communicating faster than light, rather, the very concept of distance is meaningless to them. They belong to a single, unified system, and our perception of separation is merely an illusion caused by our limited understanding of space-time. Thus, quantum entanglement might be telling us that the boundaries we perceive between objects, events, and even time itself are not as real as they appear. Shutterstock. This is a difficult concept to grasp because it upends our entire worldview. We assume objects are independent. A tree is not a stone, and a person on the other side of the planet has no direct connection to you. But entanglement suggests the separation is just a surface-level appearance. At a deeper level, the universe is far more interconnected than we realize, bound by invisible links that transcend our conventional understanding of space. Another way to look at it is that reality might not be composed of independent objects at all, but rather of relationships. In classical physics, we imagine the universe as a collection of separate entities, each with its own properties, moving through space and time. In the quantum world, these entities cannot be understood in isolation, their properties only gain meaning in relation to other objects. Therefore, the fundamental building blocks of reality may not be things, but the relationships between them. This leads to profound philosophical implications regarding the self. We are used to seeing ourselves as individuals separate from the rest of the world, but if everything is fundamentally interconnected, the boundary between self and other may not be as clear as we believe. This has led some philosophers to suggest that entanglement might offer a clue for rethinking consciousness and existence. If particles can be correlated across vast reaches of space, could consciousness also be part of this interconnected fabric? One of the most puzzling aspects of entanglement is its relationship with information. It has led some physicists to suspect that information itself, rather than matter or energy, might be the most fundamental constituent of reality. Some theories suggest the universe is built of bits of information, and entanglement is simply a window into how that information is shared on a cosmic scale. If this is true, the line between the physical and the non-physical becomes even more blurred. Unlike physical objects, information isn't necessarily bound by the same rules of space-time. It can exist in multiple forms simultaneously. Entanglement may simply be the way information operates at its most basic level. Once again, the role of the observer becomes critical. In classical physics, an object's properties exist regardless of whether we look at them. In quantum mechanics, however, the act of observation seems to play a vital role in determining the state of entangled particles. Before measurement, particles exist in a state of superposition where their properties are not fixed. It is only through interaction with an observer that these properties collapse into a definite state. Quantum mechanics and Einstein's theory of relativity are the two pillars of modern physics, yet they paint starkly different pictures of the universe. Einstein's theory gives us a smooth, continuous canvas of space-time, where the presence of massive objects causes it to curve a curvature we experience as gravity. Relativity has been incredibly successful at explaining the large-scale structure of the universe, from planetary orbits to the motion of galaxies. But quantum mechanics, which studies the smallest particles, tells a completely different story, one that challenges our understanding of space-time itself. The two theories handle space-time in fundamentally different ways. In relativity, space-time is continuous, it can be stretched and warped, but it has no gaps. Objects move through it smoothly, and the passage of time can change depending on speed and gravity. In the quantum world, however, space-time does not behave like a smooth continuum. At the smallest scales, space-time appears granular or pixelated. Particles pop in and out of existence, and instead of moving along continuous trajectories, they can tunnel or jump from one place to another. This is completely at odds with the smooth, predictable space-time of general relativity. One of the greatest challenges in modern physics is reconciling these two approaches. The most famous tension occurs at the center of black holes. General relativity predicts a singularity where space-time breaks down completely, while quantum mechanics insists that information can never be destroyed. If something falling into a black hole is lost forever, it conflicts with quantum principles. This is known as the black hole information paradox. The quantum behaviors we've discussed, like entanglement and tunneling, also defy classical views of space-time. Entangled particles act as one regardless of distance, while the bottom line of relativity is that nothing can travel faster than light. In relativity, locality is a core principle. No signal, no influence, and no signal can exceed the speed of light. Quantum mechanics simply does not follow this iron rule. Furthermore, at the quantum level, time does not behave as a smooth flow. Some physicists even speculate that time might be quantized, composed of the smallest, indivisible units, much like energy. This is a far cry from the smooth dimension of time in relativity. For decades, scientists have tried to unify the two, but a complete theory of everything remains elusive. Leading candidates include string theory, which suggests all particles and forces arise from tiny vibrating strings. In this view, space-time is not fundamental but emerges from the vibrations of these deeper strings. Another approach is loop quantum gravity, which proposes that space-time is made of tiny loops, making its fabric granular rather than smooth. If space-time is not fundamental but emerges from the quantum world, then the classical, predictable world we experience is just a shell over a much more complex reality, a world built on a chaotic, uncertain quantum foundation where causality, space, distance, and even time lose their traditional meaning. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John F. Clauser, and Anton Zeilinger. Their experimental work provided the smoking gun evidence for the violation of Bell's inequality. These experiments didn't just confirm the strange language of quantum mechanics, they changed how we understand the universe. By proving that Bell's inequality is violated, they showed that the classical view of local objective reality, the idea that objects have definite properties and only influence each other through local interactions, is not how the universe actually works. There were, back in the 1970s, when the strange predictions of quantum theory were still met with heavy skepticism, John Clauser's experimental work marked a turning point. He moved the abstract debate into the laboratory, designing experiments to verify or falsify the core predictions of quantum theory. The focus was on local hidden variables. Classical physics assumes that objects possess definite properties that don't change just because you measure them, a concept known as realism. Quantum mechanics challenges this, suggesting particles exist in a superposition of states until observed. This deeply unsettled many, including Einstein, who famously said, "God does not play dice." He believed there must be hidden variables determining a particle's behavior behind the scenes. In 1964, John Bell proposed a mathematical inequality to test for these hidden variables. Clauser and Stuart Friedman took up the challenge, performing the first direct test. They used entangled pairs of photons sent to two different detectors. According to quantum mechanics, measuring the polarization of one would instantly determine the polarization of the other, regardless of distance. In a classical world, this is impossible because no influence can travel faster than light. Their experiment showed a clear violation of Bell's inequality, meaning no local hidden variable could explain the correlation. In other words, classical mechanisms failed, and quantum mechanics was right. Entanglement was real. Clauser's work pulled quantum entanglement out of the realm of mathematical oddity and into the reality of measurable, reproducible science. This has broad implications for our understanding of nature. If there are no hidden variables, then the behavior of quantum particles isn't predetermined by any deeper classical laws. Measurement results are fundamentally probabilistic. This forces physics to step away from a deterministic universe where the past determines the present, and the present determines the future. In the quantum world, uncertainty and randomness are intrinsic properties of reality. It also highlights the role of the observer. In the classical view, measurement simply reveals a pre-existing property. In the quantum world, measurement causes the wave function to collapse, bringing the particle into a definite state. At least at the quantum level, reality does not seem to exist independently of the act of observation. By the 1980s, Alain Aspect further solidified the evidence for quantum non-locality. He didn't just replicate the experiments, he made crucial improvements to close potential loopholes that left room for doubt. Two major loopholes were the locality loophole and the detection efficiency loophole. The locality loophole suggested that if the detector settings were fixed before the particles were even emitted, the particles might somehow know the settings in advance or exchange information faster than light to fake the entanglement effect. Aspect's brilliance was in randomly changing the detector settings while the photons were already in flight. This meant the particles had no way of knowing the settings beforehand and no time to communicate. Even under these conditions, the experiment still violated Bell's inequality, powerfully ruling out local hidden variables or faster-than-light communication. Technically, this was an immense challenge. Changing settings in the tiny window of time it takes for a photon to travel required extreme precision. Aspect's team succeeded, making the experiment far more rigorous. He also improved detection efficiency, reducing the number of lost photons. This addressed concerns that perhaps only the detected photons were violating the inequality while the missing ones followed classical rules. With aspects improvements, the violation remained, cementing the conclusion that quantum non-locality is a fundamental feature of the universe. As each loophole was closed, the room for classical explanations vanished, and the quantum path became the only one left standing. After Clauser and Aspect established the experimental foundation for entanglement, Anton Zeilinger took the next leap. If particles can be entangled and share information instantaneously, could we use this principle to transport the quantum state of a particle from one place to another without any direct physical contact? The answer is yes, and this is known as quantum teleportation. It is crucial to emphasize that this is not teleportation in the science fiction sense of moving a physical object instantly, rather, it is the transfer of quantum state information at the subatomic level. Zeilinger's team used sophisticated optical setups to implement the basic process of teleportation using photons as a platform. By preparing two particles, A and B, in an entangled state and performing a specific joint measurement on a third particle, C, and particle A, the entanglement between A and B causes B to eventually take on the exact quantum state information originally held by C. Note that it is not the matter of C that moves, but the information defining its quantum state. This does not violate the no-cloning theorem, because the original state is not copied, it is destroyed at the source during the process. In 2012, Zeilinger's team successfully teleported a photon's quantum state over 143 kilometers, demonstrating the feasibility of teleportation over long distances and proving that entanglement remains robust across large scales. This laid the experimental groundwork for future quantum communication and quantum networks. It also underscores a profound idea: at the quantum level, information may be more fundamental than matter itself, and physical objects might just be the manifestations of informational structures. The violation of Bell's inequality is one of the most profound results in modern physics, forcing us to reshape our entire understanding of the cosmos. In experimental tests of Bell's theorem, the measurement results of entangled particles show a correlation that exceeds what any local hidden variable theory could allow. We are forced to choose between two seemingly unacceptable conclusions: either we abandon locality, or we admit that the universe operates in a way far weirder than we imagined. To use a metaphor, imagine flipping two coins at a vast distance from each other. Classical intuition says their results should be independent. Over time, you'd see a predictable mix of heads and tails. But if every time you flip them, no matter how far apart, they both showed the exact same result, it would suggest they are linked in a way that is classically impossible. This excess correlation is exactly what we see in entanglement measurements. The violation of Bell's inequality doesn't just challenge locality, it supports a view that, at the most fundamental level, reality is not made of stable, definite objects, but of probabilities and relationships. Particles only seem to choose their state when observed. Before that, their properties exist in a kind of flux. This raises a haunting question: if particles have no definite properties when unobserved, what does the universe look like when no one is looking? Does the moon exist when no one is watching it? These questions, though they sound philosophical, stem from hard experimental data. The violation of Bell's inequality forces us to face the possibility that observation is not just a passive process of gathering information, but an active process of participating in the creation of reality. At the core of this is non-locality. In classical physics, an event in one location cannot instantly affect something far away. The speed of light is the ultimate speed limit. Yet at the quantum level, entangled particles exhibit an instantaneous correlation without any identifiable physical signal traveling between them. This isn't communication in the traditional sense, but the correlation between the two particles is undeniable and faster than light could ever travel. This is the essence of non-locality. An event here can have an immediate correlation there without any visible physical connection. This pushes us down two counterintuitive paths. Either the universe is deeply non-local, where events are instantaneously linked across space, or the universe simply doesn't exist in the way we traditionally understand. If we take non-locality seriously, it means the connectivity of the universe transcends classical understanding. Rather than objects being separated by distance and moving linearly through time, particles can exist as part of a whole that bypasses spatial constraints. Non-locality suggests that information or influence can be shared faster than light, even if it's not the kind of controllable communication we can use. This hints that our intuitive view of space-time is incomplete. Perhaps space-time isn't the fundamental building block of reality, but a property that emerges from a deeper layer. Another even more radical idea is that space itself might be an illusion, or at least, not fundamental. The distances we perceive might be more like a byproduct of how our brains process information rather than a true property of the universe. This would explain why distant particles show such strong correlations. At a fundamental level, they aren't actually separated by space. Space is just a structure emerging from underlying quantum reality. Even more unsettling is the possibility that reality is observer-dependent. Quantum mechanics leads some to question whether reality is objective or if it relies on observation. If particles have no certainty before being observed, then does the universe even exist in the same way when no one is watching? Reality might not be independent of us. It might be co-constructed through interaction. This doesn't mean nothing exists if we don't look, but it challenges the traditional view of the universe as a stable, objective entity indifferent to our presence. Different interpretations of quantum mechanics offer different takes on this. The Copenhagen interpretation leans toward uncertainty before observation, while the many worlds interpretation suggests that every possible result of a quantum measurement actually happens, but in different, branching parallel universes. In this view, we don't force a particle to choose a state, we simply find ourselves in one of the many branches. This avoids the awkwardness of observer dependency, but at the cost of accepting infinite parallel worlds. Alternatively, Bohmian mechanics tries to preserve objective reality by suggesting particles always have definite positions but are guided by a non-local pilot wave. This restores determinism but requires accepting a wave that we cannot directly observe. Schrödinger's cat forces us to look directly at this absurdity. If macro-objects can also be in superposition, then the entire universe might be in a state of superposition. This means the universe we experience is just one projection of countless possibilities. Parallel universes follow different outcomes of the same quantum events and exist side by side, though we don't observe them. If every quantum event branches, then in one universe the cat is alive, and in another, it is dead. These realities are equally real, we only experience one because our observation anchors us to that specific branch. This brings us back to the definition of existence. If something can exist in multiple ways simultaneously, what does existence even mean? If the universe itself is in a superposition of states, our concept of being becomes slippery. Are all versions of the universe equally real, or is the one we observe special? Since its inception, the idea of parallel universes has captured the human imagination. Many worlds claims every possibility happens, if you choose to turn left or right at an intersection, the universe branches into two versions. It offers an elegant everything happens explanation for superposition. But there is also the view that reality itself is a mirage, that the world we experience is just a projection created by observation. Which is more plausible? Both challenge our intuition. Many worlds says reality is much larger than we thought. The mirage view says reality isn't what we thought it was at all. Many worlds is almost comforting in its order. All branches follow the same physical laws. The mirage view is more disturbing, suggesting our intuition of a stable world is just a convenient fiction. In many worlds, the observer just follows a branch. In the mirage view, the observer is active without an observer. There are only never collapsing probabilities. So, the question remains, when no one is looking, does a world independent of us exist? Quantum decoherence is the bridge between quantum weirdness and macro stability. It describes how, when a quantum system interacts with its environment, it loses its quantum coherence and starts behaving like a classical system. Simply put, decoherence explains why we don't see chairs in two places at once. Any tiny interaction with the environment washes away the superposition, making the system appear to be in one definite state. The key distinction is that decoherence is a physical process, while wave function collapse is a theoretical description. Decoherence explains why we don't see the superposition, but it doesn't strictly answer why one specific result is chosen. That is where the interpretations diverge. Many worlds sees decoherence as the separation of branches, while Copenhagen sees it as part of the process leading to a single outcome. Decoherence also presents a practical reality. If a system is isolated enough, it can maintain coherence for a long time, showing macro-scale quantum effects. This is the great challenge of quantum computing. Qubits must maintain coherence without environmental interference, or the calculation is destroyed by environmental measurement. As we dive deeper into quantum theory, a seductive thought emerges: the most fundamental thing in the universe isn't matter, but quantum information. Classical information is measured in bits, quantum information is measured in qubits, which can exist in a superposition of 0 and 1. This gives quantum information properties that the classical world lacks, such as the no-cloning theorem, which prohibits the perfect copying of an unknown quantum state. This suggests both the fragility and the primacy of quantum information. In this view, atoms and objects are not the floor of reality, but rather the manifestations of deeper informational processes. Information flows through entanglement, unconstrained by traditional space-time. This might mean that physical objects are just the hardware carrying the informational software. This line of thinking echoes the holographic principle from black hole physics. If information is never destroyed, then information falling into a black hole must be preserved. Theory suggests it is encoded on the event horizon, a two-dimensional boundary that preserves all the information of the three-dimensional interior. If we extend this principle to the entire universe, the three-dimensional reality we experience might just be a projection of a lower-dimensional informational screen. Furthermore, some researchers are attempting to find experimental evidence of the pixelation of space. If space is composed of discrete units of information, it might reveal its pixels under extreme magnification, much like a digital image. This leads us to the holographic principle. Born from the black hole information paradox, this bold theory suggests that everything happening in a three-dimensional volume can be fully described by information encoded on its two-dimensional boundary. When extended to the AD/CFT correspondence, we find a profound framework where a higher dimensional theory with gravity is equivalent to a lower dimensional quantum field. Theory on the boundary. This provides deep insights into quantum gravity and black hole thermodynamics. If our universe is indeed holographic, the 3D thickness we perceive might be nothing more than a projection of 2D informational sheets, an incredibly high-fidelity cosmic hologram. Quantum field theory tells us that the vacuum is far from empty. Various quantum fields fluctuate constantly, with virtual particles popping into and out of existence. Although we cannot catch a virtual particle directly, we can measure their effects. A famous example is the Casimir effect, where a measurable attractive force is generated between two unchanged arced metal plates placed extremely close together. This force arises from the difference in vacuum fluctuation modes between and outside the plates. In quantum electrodynamics, QED, electromagnetic interactions between charged particles are viewed as the exchange of virtual photons. In quantum chromodynamics, QCD, the strong force that binds quarks together is seen as the exchange of gluons. This means the fundamental forces that build our world are, in a sense, mediated by entities that are not fully real in the traditional sense, making the definition of reality even more subtle. If something so fleeting can influence measurable results, is it real? Or perhaps, is reality simply defined by its contribution to an outcome? The idea of a vacuum filled with fluctuations makes the concept of nothingness impossible to maintain. Even in a place where there is supposedly nothing, there is a hidden current of activity. So, what is the baseline of existence? Perhaps the solid matter we perceive is merely a temporary configuration of deeper quantum information and fluctuations. Max Tegmark, a Swedish-American physicist, proposed a daring hypothesis that challenges our very grasp of reality, the mathematical universe hypothesis. He argues that the universe isn't just described by mathematics, it is mathematics. This viewpoint elevates mathematical description to a radical new level. Everything we perceive as real, from the stars in the sky to the atoms in our bodies, is ultimately a mathematical structure. For Tegmark, the physical universe is simply an abstract mathematical object. Tegmark's theory challenges the common assumption that math is just a tool we invented to map the world. In physics, we use equations and formulas to predict the behavior of particles, forces, and energy. We usually believe these structures describe independently existing physical objects. Tegmark, however, argues the opposite. Mathematical structures are the fundamental reality, and physical objects are merely the manifestations of these deeper mathematical truths. At the core of his thought is the idea that all reality can be reduced to numbers and their interrelationships. The laws of physics, from those governing galaxies to those ruling subatomic particles, are all expressed mathematically. Einstein's famous equation, $E equals mc²2, isn't just a description of energy and mass, it is a statement of the fundamental operational mode of the universe. According to Tegmark, these equations don't just describe the world, they are the world. The universe doesn't just follow mathematical rules, it is a mathematical structure in itself. In everyday experience, we tend to think of physical objects as the most real things in the universe. A tree is real because we can see it, touch it, and interact with it. But in Tegmark's framework, that tree is nothing more than a collection of mathematical properties. Its shape, its dimensions, and even its color can be described through geometry, numbers, and equations. The tree as a physical object is just an embodiment of the underlying mathematical structure. In this sense, physical objects have no existence independent of their mathematical descriptions, they are simply one way that mathematical structures express themselves. Tegmark even suggests that if the universe is fundamentally mathematical, then every possible mathematical structure may exist as its own universe. In his vision, every self-consistent mathematical structure corresponds to a different universe. The laws of physics in those universes might be vastly different or entirely unrecognizable to us, but they exist simply because they are mathematically consistent. In our daily lives, we draw a sharp line between real things and abstract things. However, Tegmark's hypothesis suggests this distinction is an illusion. If the universe is fundamentally mathematical, then numbers and abstract objects are just as real as physical ones. The number 2 might be just as real as the chair you are sitting on, they simply belong to different types of mathematical structures. If everything is essentially math, then our perception of reality is just a specific interpretation of these structures. When we look at a tree, we see an entity with color and texture because our minds process information in a way that is useful for our survival. This doesn't mean the tree exists physically in the way we perceive it, it is merely the manifestation of the underlying mathematics. And that brings us to the end of our journey for today. I hope these insights spark a sense of wonder in you. Thank you for sharing this time with me. I wish you all beautiful dreams and a wonderful day ahead.